Hello and welcome to episode 2 of Packet Tuesday. My name is Johannes Ullrich, and well, after talking about DNS last time, I figured let's continue that conversation about DNS a little bit. But this time, not a sort of obscure feature like Punicode, but let's talk about something more common. DNS options, in particular, extended DNS option 0. Now, before I dive in here, first of all, thanks to everybody who subscribed and liked and sort of did their thing to help me here with YouTube. I do it, well, because people are listening, because people are watching it. Also, keep the feedback coming, please. I'll make adjustments to it. I got a little bit less shaky sort of overhead camera here, so hopefully this will work out quite well this time. Again, there will be links in the show notes on YouTube, also packettuesday.com. If you go to that website, it'll always have the latest video right up there. Now, with that, let's talk a little bit about extended DNS option 0 and where it all comes from. And to do this, let me just quickly switch here to the whiteboard and make a little bit a sketch here, showing you a bit how this all works. So typically you have your client and it sends a request to a server. Let's say this is your a query for sans.edu. So that's the query we are sending. This is one UDP packet. And then we have a response coming back in the form of a UDP packet. This is the address of sans.edu. This is all good and fine, and that's usually works just great. But there is a potential problem if these DNS responses are getting too large. The original DNS RFCs only allowed UDP responses for up to 512 bytes. And the reason behind this was that they did try to avoid fragmentation. And you need at least an MTU of 576 to do TCP, so 512 pretty much always works. And but what if you have more than 512 bytes of data to send? So what happens in this case is we're again sending the same query here, or a query as a UDP packet, and then a response is coming back with some answers and a truncate flag set. This truncate flag will tell us that, hey, the response was too large, didn't fit into 512 bytes, so now you have to come back via a TCP. So what happens next is your TCP SYN, then the SYN-ACK, then you have your ACK, then you have your query, and then you have your response, however many packets that takes, and then you have your, your FIN-ACK, FIN-ACK, ACK, whatever. Actually, other way around here. So what was 2 packets here with UDP all of a sudden became 1, 2, 3, 4, 5, 6, 7, 8 packets. So we have now 8 packets instead of 2. Highly inefficient. And so we really want to avoid that TCP part if we can help it. Now, originally, 512 bytes was okay for UDP. We actually, limited the number of root name servers to 13 because those 13 host names and IP addresses just fit into 512 bytes. But as the internet evolved, we added stuff like IPv6, we added DNSSEC most of all, that made those responses larger. And it would have become really common to have sort of that fallback to TCP. Which causes all kinds of other issues. So to prevent this, we introduced now the EDNS, extended DNS option 0. And what this is as I'm sending my query here, I'm including an option that says, hey, you can actually send me, 4 kilobytes as a UDP response, and that's actually a quite common number. If you're doing DNSSEC, you must support EDNS 0, but most name servers these days support EDNS 0, even if they are not necessarily dealing with with DNSSEC. So let's see how that works. Let's switch here to the screen share. Let me just wipe the whiteboard, and let's start up the terminal here. Okay, let's just do a little dig for the name root server, so that priming response, it's sometimes called, that returns all the root name servers. And you see, it is actually here already now 823 bytes for this response. So 823 bytes would not have fit into your normal default UDP response. If I go back up here a little bit, you'll see that my client here actually suggests that you can send 1024 bytes back, so 1 kilobyte. So this came back as a UDP response, this particular packet here. Okay, so this is one reason we need it. But then again, Packet Tuesday, we want to look at packets. So let's capture some packets here and see what this looks like, sort of on the network. Now, as usual, and I think I explained this last time, when I acquire packets here, I'm always acquiring all packets. I'm not doing any filtering here. And let's just write it like this and put it in the background. Okay, this looks fine. Now let me just run that dig for the root name servers again. Okay, here we got it. Let's get the TCP dump here, exit it, and now let's actually dive in and see what these packets look like. Okay, yeah, so we have a bunch of other stuff happening here, of course. Then let's do a filter now. And always filter later after I have the packet capture, because that way if I mess up my filter, I can always write a different filter. While if I write the wrong filter as I'm collecting the packets, well, there is no sort of easy coming back. But anyway, so here is our PCAP, and actually we're lucky here. It was the only DNS query and response we had. So let me just make it a little bit easier and write this into a new PCAP file, and this will be the PCAP file that I'll then attach to the video. So it just has these two packets here. Let's take a look. Yeah, has just these two packets. Hey, IPv6, so something else a little bit different from last time. When we looked at packets last time, we had IPv4. But really inconsequential here. This works with IPv4 as well as IPv6. And well, let's actually now just look at the first packet and get the hexadecimal output here. So this is our first packet. And then let me actually just pop up also a cheat sheet here for IPv6. Yeah, that should do it. Okay, And then we need our IP header. So this is our IPv6 header. Starts with 6. So let's move over here. So let me actually make this just a little bit prettier here. Good. And so IP version 6. Then this 0 here, this is now the traffic class, similar to the type of service in IPv4. Notice we don't have a header length here. The IPv6 header is always fixed at 40 bytes. In IPv4, we first had our version, 4, of course, for IPv4, followed by the header length in 4-byte increments. So 4.5 is typically the first byte of the IPv4 header. In IPv6, we just have the 6, and then this traffic class sort of bleeds in here into that byte, in that we have this here as our traffic class. The next, we do have a flow label. This is something that does not exist in IPv4 in this form. It's meant to label, well, as the name implies, kind of traffic flows. So data going from one host to another host as part of a connection, that would be labeled like this. It's just a random number as far as we are concerned. It's not the IP ID. That would be sort of the closest thing kind of in IPv4, but it's different from the IP ID. We still have sort of an IP ID fragment IP in IPv6, but it's not part of the IP header. Next, we have our payload length. Subtle difference here in the payload length. In IPv4, it was the datagram size. The datagram size included the IP header length. In IPv6, it does not include the IP header length, so this is just anything beyond the IP header. 2 times 16, so 32 plus 4, that's 36. So 36 bytes of data. And then you have, of course, the 40 bytes of the IPv6 header there as well. Okay, then next we have our next header, protocol 11, that's UDP, that's typical for DNS. Then we have our hop limit, 40 or 64, typical starting hop limit here. And then we have our IP address, the source IP, you see the 2603, all the way to the Charlie 9 Delta Charlie here. And then our destination IP, that then concludes the IPv6 header. And my recursive DNS server, well, the last byte of the IP address is 35 or decimal 53. It's sort of a little hint for me. Okay, now this is the DNS server because the IPv6 address ends in 53 or 35 in hexadecimal. Okay, so that's our IPv6 header. Moving on, we now have a UDP header and DNS payload, and they don't really change when it comes to IPv6. They sort of remain the same. So let me just take a little bit of different color here for that. And here we have our source port. Some high source port here, 52,327 apparently. Then we do have our destination port 53, which is typical for DNS. Then we have our UDP length 24, which is identical to the payload length because the UDP length includes the UDP header. So for UDP and IPv6, if you don't have any extension headers, anything weird going on, the UDP length equals the payload length. And then we have our UDP checksum, which is also the only checksum here in the packet because there's no checksum for the IPv6 header. Okay, so this is our UDP header. And now the only thing left is the DNS payload. So DNS payload are these last 2 lines here. Starting with the query ID, 1188, just a random number, hopefully random. Then we do have our flags. Now we have two flags set here. The first flag, the lowest flag of that upper flag byte, just means recursion desired. So basically, yes, we want the recipient to do recursion for us. We are sending this to a recursive name server, so that's all good. And then the 2 here is the authentication flag, or authentication domain, something it's called, or AD flag. What this means is that I tell the name server, the recursive name server, hey, could you please do all the DNS stuff, the DNSSEC stuff for me, and validate that the DNSSEC response is valid, and only forward a response back to me if that all works out okay. So that's what the 2 is about here. And then we have our number of queries, 1 query. No answers, no authority records. And then here as additional records, we do have 1. And that's sort of where our options then come in. The options, these DNS options, they're essentially encoded as an additional record in a query. Typically, you may have seen additional records in a response. That's, for example, for the name servers where you have our IP addresses. But here we actually do have additional records in the query, but they turn out to be options. Okay, now next we would have our label, but since we just looked for dot, there's nothing here. So we do have just 0 here. There's basically nothing. So this is basically just means the dot. There's nothing there. Then the type, we're looking for an NS record, type 2. And then the class is 1, which means internet. Okay. So this is our query. And then we start having these additional records. And these additional records now are the DNS option. So let's quickly switch over here to the RFC and take a look at how this encoding works. The options, we start with a name, just like anything in DNS, and we just use 0 here, just like what we had here for the root DNS servers. There's nothing really in the domain. Then we have a type. And type 41 means that this is an option, followed by 2 bytes for the actual UDP payload size that we are allowing here. So okay, let's go back here and take a look at our packet. So we got 0, then we got 29. Now, 29, 16 times 2 is 32, plus 9 is 41. That's our option, 41. And then we have 1000 as the allowed UDP size here. Let's just convert that quickly here to decimal. So yeah, 4096 bytes. That is the allowed UDP response size that we have. And like I said, 4 kilobytes is often the default. Personally, I always limit my DNS servers to a kilobyte because that way I still avoid fragmentation issues, and 1 kilobyte is usually good enough for most DNS responses. But this came now from my Mac client, not from a DNS server. That's why you see the 4 kilobyte here. The rest is 0. The rest is really not used here. But we can actually have tcpdump help us with this a little bit. If I add some verbose flags here to tcpdump, then tcpdump will decode these options, and you see here UDP size is 4096. So basically meaning we don't need to worry about any switch to TCP here. Let's just take a look at the second packet here. That was the response. I probably need to less this here, yeah, because it's getting pretty big here. So here we have all the root DNS servers coming back. We got 13 answers. These then 0 authority records and 27 additional records. So these 27 additional records are now a mix of these clue records, basically IP addresses for the individual DNS servers. And in the end, we actually then have again this UDP, this option, DNS, extended DNS option size 0. Here, 1 kilobyte. Like I said, my recursive name server sort of like 1 kilobyte. So this is just echoed back here. What's the maximum size that the server would actually be using? The client offered, hey, you may use up to 4 kilobytes, but what actually the server then says, yeah, it's fine, cool that you want to do 4 kilobytes. I'm only going to do 1 kilobyte. In this case, that's plenty, and you don't have any issues here. Our total payload length here is 831 bytes. So just to summarize quickly, in the old days, DNS responses over UDP were limited to 512 bytes to avoid fragmentation. With IPv6 and with DNSSEC sort of being more used, that turned out to be very inefficient and not really what we wanted to do. So this extended DNS option type 0 was introduced, which allowed the client to signal to the server that the server may send more than these 512 bytes in a UDP response. The server doesn't have to take advantage of this. The server may decide, like here, to clamp it down to a smaller UDP response, but the server has the option to send up to 4 kilobytes in one UDP packet. It still has to be one UDP packet. So what you end up here is often fragmentation, where you do get then multiple packets back that are part of the same DNS response, part of the same fragmented DNS packet. And it's sort of one of the cases where even in modern networks, with all the fragmentation avoidance that's happening, you still get some fragmentation. Anyway, so this is just what I want to show you here. Just a little bit more DNS, extended DNS type 0. If you have any questions, please send me an email. Use the contact form on Internet Storm Center website. You'll find my email address also on the packettuesday.com site. I think I didn't put the @ symbol in there just to cut down a little bit on the spam. I already get enough spam, so it shouldn't really make a big difference. But yeah, feedback is very welcome. Subscribe, like, recommend your friends and enemies and everybody to watch these videos. I'll try to keep them going one a week. Thanks.